So last time we conceptually introduced MCMC. What we should be doing right now is sort of, thinking about a very concrete type of MCMC implementation. So MCMC samplers. There's two broad family of samplers that we'll be discussing. One of them is the Gibbs sampler, and we will exclusively be using it for high-dimensional distributions. And the other one is the Metropolis-Hastings sampler, which works for both multidimensional and single-dimensional distributions. And in fact, Metropolis-Hastings can also be used within Gibbs. But let's start off with the slightly more general Metropolis-Hastings sampler. When Metropolis-Hastings, I should say that Metropolis-Hastings is, like MCMC, it's kind of brute force. You can use it all the time. Gibbs sampler will require some requirements in order to be able to use it. But if you happen to be able to use it, it's going to be much more efficient. So, first things first, I can define my probability, my target distribution. I'm going to define it as some pi hat divided by some pi hat. This is essentially the unnormalized target distribution, and the pi here is the normalized, I should say density technically. This is the unnormalized density, and this of course is the normalization constant. The normalization constant is generally going to be a very annoying integral that you'll have to take, and the good news is that neither the Gibbs sampler nor the Metropolis-Hastings samplers require you to work with pi of r. They're okay with you having an unnormalized density. So generally speaking, if your density, for example, is a Gaussian, which of course you can easily normalize, but if it were a Gaussian and you're trying to draw these samples r, then you don't need to know what this coefficient is, which is independent of r. So let's talk a little bit about the Metropolis-Hastings sampler, which is an example of an MCMC sampler. So by MCMC sampler, again, we mean that our samples are going to be correlated and they will form a Markov chain. And Metropolis-Hastings will be one particular way in which to create that Markov chain, which again satisfies all four of those requirements. So let's go ahead and write down the algorithm for Metropolis-Hastings. So first thing is that you need to have a target distribution, or if you can't normalize it, that's perfectly fine, an unnormalized target distribution. Then you will also need a proposal distribution. And what we're basically saying here is that the proposal distribution is a function of r proposed given an r old. So you can think of this as a distribution of r proposed given some r old. So r old here is given as a parameter of this distribution. R proposed is its variable. So for example, a Gaussian centered at r old, just like the example we had looked at sort of previously. And the third thing you need is the r old, right? You need to know where to start or where you want to start. And again, determining where you want to start can be a bit of a big deal. So step number one, generate an r proposed from your Q distribution, which depends on parameters like r old. Then compute the acceptance ratio, which we'll talk about in just 1 second, and that acceptance ratio is A of r old, r proposed. So we'll have to, again, we'll define this in just 1 second. Then generate, don't know why that line came up, then generate a U drawn from a uniform distribution between 0 and 1. And now if U is less than or equal to A, then set R new equal to R proposed. And otherwise, R new equals R old. So, just to re-summarize, you start off with a normalized or an unnormalized target, your proposal distribution, as well as a starting point. You generate your R proposed from your proposal distribution. You compute the acceptance ratio, and you also simultaneously generate a uniform random number. So if your acceptance ratio happens to be, let's say, 10, then your uniform random number will always be less than 10, then accept the move. If your acceptance ratio, for example, is 0.1, and by chance you happen to draw a uniform random number which is 0.05, then that's great, accept it again. But if your acceptance ratio is 0.1 and the uniform random number you draw is 0.5, then you have to reject, and R new becomes R old. What is the acceptance ratio? A of R old, well, I should say A of R proposed, that's the variable, R old is the parameter, is going to be the following. It's going to be the ratio of R proposed over R old multiplied by the ratio of target distributions with sort of arguments swapped. Okay, first things first. Why do we not care about normalizing our target distribution? Well, the only place in which the target distribution appears in my Metropolis-Hastings is in my acceptance ratio. And my acceptance ratio considers ratios of my target distribution. So any constant with respect to R cancels out anyways. So if I choose to normalize it, that's great, but I'll be doing a lot of extra work because that normalization constant will cancel out. Okay. Let's suppose that I just focus on this portion here. Suppose that this is my target distribution, pi of R versus R. So it's a simple target distribution, kind of looks like a Gaussian. I start off from some R old, and I propose something which is here. Well, immediately, I notice that pi of R proposed is going to be a lot bigger than pi of R old. So my acceptance ratio is going to get larger, and it will be harder for the uniform random number that I draw between 0 and 1 to be smaller than this. In fact, this can exceed 1. So if the R proposed divided by R old is greater than 1, which means that I'm going towards a higher region, I always have to, if I consider exclusively this term, I accept. What if I choose an R proposed which is going downhill? So it's lower in terms of pi of R than I previously was. So I'm here and I propose this instead. So let's get rid of this one here. Whoops. What happens then? Well, maybe the ratio of pi of R proposed to pi of R old is going to be like 0.5, meaning that I've dropped by, a factor of 2. That's fine. Maybe the U that I draw is less than 0.5, and maybe I accept this move, even if it's going sort of in the wrong direction. Why would I want to move in the wrong direction? Again, my distribution needs to be stationary, and I need to be able to propose things both going in the right direction and the wrong direction, because the wrong direction maybe leads me to another region of pi of R, which is even higher density than this one here. I don't know yet until I explore this density, right? So let's go ahead and remove that. Great, so this term controls the flow from R old to R proposed. Oops, these dots here. Let's remove all these circles that I drew. Now let's focus on this other term. This other term basically tries to balance the flow from R old to R proposed by basically telling you that, well, maybe some bias could have been introduced by the proposal distribution pushing you in a particular direction. So you kind of want to reweight that by the ratio of how likely your proposal distribution is to have taken you there. So in some sense, you can think of this term as controlling the flow from R proposed back down to R old. So this is the acceptance ratio that you use in Metropolis-Hastings. Let's look at a very simple, well, a simple example, but in fact not so simple. Let's suppose that I try to draw samples from the following pi of r. Imagine I have a Gaussian, but that Gaussian is very unusual because it doesn't have a tail, so it's a truncated Gaussian. So if I were to erase the first line I drew, it's something that looks like this. So my pi of r, mathematically, and I should really say my pi bar of r, is going to be 1 over square root 2 pi sigma squared. It's just going to be plain old Gaussian. For some r greater than or equal to, let's say, 0. So maybe this here is the origin. And it's going to be 0 for r less than 0. So it's a Gaussian for greater than 0. And maybe the Gaussian is centered at some positive value, right? So this is 0, this is mu. So the Gaussian is centered at some positive value, and it doesn't have a negative tail. So you're going to say that doesn't look very complicated. It's just a plain old Gaussian. Actually, it's not. And in fact, you can't do Box-Mueller on something like this. So even something this simple actually requires Metropolis-Hastings. So here's what we're going to do. We're going to suggest an R naught. We have our pi hat. That's the expression that I wrote above. And we're going to have a Q of R old, R proposed, which is going to be a normal whose variable, again, is going to be R proposed. It's going to be centered at R old, and it's going to have, and it's going to have a variance of lambda squared. So let's just stop and think about this for just 1 second. We're going to propose some initial value, presumably some positive initial value, and then we're going to propose something. This Gaussian here is going to be centered at this value with some variance. So maybe my proposal distribution looks something like this. It's normalized, so maybe it's a little bit higher. Maybe it's something like this. Great. My target distribution only has density from 0 to infinity, but my proposal distribution has density here at the normal from positive infinity all the way out to negative infinity. So it's possible that I propose negative values. What happens then? The density does not have negative values. Well, remember the acceptance ratio, R old, R proposed, is proportional to pi of R proposed. Now, if I propose negative values, then my acceptance ratio is simply 0. And if I draw a uniform random number between 0 and 1, and my uniform random number cannot be less than 0, and therefore this move is always rejected. So in other words, the system internally is kind of making sense. It may be inefficient to be using a target distribution that does not have the same support, or be using a proposal distribution that does not have the same support as my target distribution, but as long as it has support in the region in which my target distribution has support, then in principle I should be able to explore my target distribution, even if some samples that I propose that go beyond the target support are always rejected. So if that's the case, then I can go ahead. I know what my target distribution is. I know what my acceptance ratio is. We wrote down the expression last time. So I can go ahead and write down my A of R old, R proposed. And that's going to be equal to, let me go ahead and write it down, and then we can talk about it for just 1 second. That's R old minus mu squared minus R proposed minus mu squared divided by 2 sigma squared. And this is for R proposed greater than or equal to 0. And for R proposed less than 0, we already said that the acceptance criterion is 0 because R proposed, pi, sort of R proposed is 0. Okay. Now I can run my Metropolis-Hastings. But before we run the Metropolis-Hastings, we need to ask a question. This looks a lot like the ratio of pi R proposed to the ratio of pi R old. What happened to the ratio of the proposal distributions? So again, this is exactly, in fact, the ratio of pi R proposed to pi R old. That's why you have a minus here and you have a plus sign here. So what happened to the ratio of the proposal distributions? The proposal distributions were Gaussian. If we remember, our Q was proportional to an exponential of R old minus R proposed. And this thing, this thing is squared. And there's a minus sign here, and that's lambda squared in the denominator. So the ratio of proposal distributions is 1, because if I swap this for this and then I square it, I get exactly the same thing back. So the R proposed, or I should say R R prop R old divided by R old R prop is equal to 1, because those two distributions are the same. It's a symmetric proposal distribution as I swap R old for R proposed and R proposed for R old. So then the ratio, or the acceptance ratio, simplifies to just the ratio of target distributions. I don't need to write multiplied by 1. It's clear. This very specific case of selecting a symmetric proposal distribution, symmetric with respect to sort of R proposed and R old, where the ratio of proposal distributions cancel, is called Metropolis sampling. So more generally, when our proposal distributions don't cancel, and our acceptance ratio can be written as a ratio of target distributions and a ratio of proposal distributions, we call that Metropolis-Hastings. For the very special case where the proposal distributions are symmetric and the ratio is 1, we typically call that Metropolis sampling, but not super important. So, great. At this point here now, we also have our acceptance criterion. So, recall, our goal was to draw samples from this distribution here. We have the acceptance. We can start off with a feasible R0, in other words, not an R0 which is negative. And we can start off with a proposal distribution. We have. And at this point, we can run Metropolis-Hastings for this very simple example. We show a demonstration of it, and I think in the textbook, and I think it's kind of worth as well exploring sort of what happens. If my proposal distribution, so suppose that this is my R0, right? This is going to be my R0. Suppose that my proposal distribution has a huge variance. So I start off here, and I propose a point with a huge, again, the proposal distribution has a huge variance. So the next point I propose is perhaps way out here, or alternatively way out here. Then what's going to happen is that I will reject that move. And I'll keep on rejecting and rejecting and rejecting and rejecting. So at some point, I should start thinking maybe my variance is too big. And because my acceptance ratio is just too small, and I keep rejecting every move. Now, sometimes people say that, for an ideal Monte Carlo sampler, your acceptance, should be somewhere between 20 to 50%, let's say. But, the goal is not to have the acceptance be 10 to the minus 6, which it would be if the variance is absolutely enormous. Okay, what if I make my variance extremely small? Then yeah, I will be accepting practically every move, probably 50 plus, or 50 odd % of them. So maybe my next move will be right over here. Again, I'm saying my variance is very small. And then my next move will be right here, and then the move after will be right there, and so on and so forth. But the problem is that I'll never get to explore this distribution. So suppose that this is the distribution that I want to explore. And I know that this looks a little bit complicated, but what I'm going to plot here is my samples, or my sample index. In other words, my first sample, my second sample, my third sample, all the way to big J samples, versus the sample itself. Now, if my sampler is good, then maybe my first sampler's here, my second sampler's here, my third sampler's here, and I get stuff that kind of looks like this. And if I histogram these samples, then I get something. So if I histogram all of these guys and put them in the right bin, then I get something that looks very much like the target distribution. Now, what happens if my lambda is huge, right? So let's erase as much of the stuff as we can. What if my lambda is huge? Okay. So the variance in my proposal distribution is just enormous, right? So I'll propose something. So, this is my first sample. It's right here. I propose something, which is way out there, gets rejected. So my R new is my R old, and I stay here. Then I propose a next sample. Again, way out here, it gets rejected. So my R new is my R old. And so what happens is that I keep getting rejected. Every so often I accept something, and then I keep getting rejected again, and I kind of stay there. So this is for large lambda. So if I ask, okay, I histogram my samples, what do they look like? Well, not great. I'm going to have one sample here and another one there. That doesn't look anything like my target distribution, right? The histogram of those data don't look anything like my target distribution. Okay, well, what if I have extremely small lambda? Right, just to go back to the example that I gave earlier, then I'll pretty much be accepting a lot of my moves. So I'll be here, then here, then here, and I'll accept the next one. This is small lambda. So sort of a small variance. Then here, then here. So if I histogram my samples, then this is what it's going to look like, perhaps. You're going to say that's all great, but I never even discovered that I had density here because I was too conservative in my search. So somewhere between the enormous lambda and the small lambda, given sort of the nature of the problem, is probably the right compromise that allows you to sort of explore much more efficiently the entirety of the target distribution. So we'll be exploring more of these topics next time, in addition to eventually developing GIP samplers. Thank you.